Hello from our charts. In this channel I show cool posters I made for mathematicians. But why should you use posters when you learn or teach? Mathematical logic. Everyone's most favorite subject. Or is it?
The subject is a joke. First order logic, second order logic, joke order logic. I'm telling you, the joke professor is not going to make a joke out of me. I'm not joking. I swear I'm never going to see the joke subject after I pass the joke exam.
That was a student's testimony. But surely, experienced professors think differently, right? Let's read a passage by Donald Kahn. But this writer, who personally met many mathematicians from the most distinguished professors to beginning students, has observed that most practicing mathematicians give little or no thought to the foundations of the field once they begin their research work. While it may be debated as to whether this is healthy, logic and foundations do not at present figure in the everyday thoughts of most mathematicians. What might be the difficulty? Maybe the problem is that the subject is presented like this. Whoa, I cannot even look at it. And that is from my own paper. But now check this out. At once you can see how multiple aspects fit together. For example, you immediately see, illustrated by a pegman, that no undecidable complete theories that are recursively enumerable exist. Stack Exchange is full of questions from people confused about the relationship, and you have it here all with examples. That is why we need to put posters to mathematical education, so the subject is loved as it should. So get the posters for your studies or students. Another cool thing about the poster is that it visually expresses the place of Gödel's first incompleteness theorem, a great far-reaching result that is also often misunderstood. The theorem ultimately implies that we cannot have a theory strong enough for doing arithmetics, that you can also algorithmically write down, that is the meaning of recursively enumerable, and that would be also complete. That was a big letdown, as once humanity hoped that there would be such a theory. Fortunately, there are cats. Nevertheless, there is a theory that can do arithmetics and is complete. You just cannot write it down algorithmically. It is the full theory of the usual structure of natural numbers. On the other hand, we have many theories that are complete and recursively enumerable. The theory of real closed fields, which is the full theory of the usual structure of real numbers, is rightly proud to be such a theory. After all, thanks to that we have an effective algorithm that can for each sentence of the traditional Euclidean geometry, but also of the relativistic hyperbolic geometry, decide whether it is provable in the theory or not. We call such theories decidable. The only problem is that we cannot do arithmetics in them. This might be surprising to learn at first, but this theory of real closed fields does not have any fancy functions included, and you just cannot define natural numbers with addition and multiplication alone. If you add a sine function, the situation would be different, but then the Gödel's result would apply. As still unanswered is whether adding exponentiation as this fancy function can get us a decidable theory. Alex Wilke gave a partial positive answer that made him quite famous. I know him personally. He was on one occasion my yoga partner. Who had such an experience with a celebrity? If you wish to get famous, you can try to answer one of the open questions of decidability. And here you have it, decidability of first order theories in one math chart. Best wishes from our charts.